I'm Manuela Balsarolo from the University of Viterbo, and I'm the chair of this session on data management and exchange. And the agenda of this session, in the agenda there are different talks on the organization of the data, hyperspectral data in geochron by John Gammon, Specchio experience by Andreas Uni, and I will do a talk on IMEC Ikos portal, and Shuretz will give us some information about the consideration for Specnet. So,
what I'm going to talk about here is actually it's a presentation Gilberto Pastorello was going to give, and he's not here, so I'm giving it on his behalf. And currently Gilberto worked on the GeoChronos project, and he's currently working in my research group. His background is computing science, and so this is an effort in data management and informatics, and it includes an emphasis on spectral data, among other things. So what are the lessons that we learned from this project? And then where are we going from this project? What can we learn and apply to Specnet-Eurospec and future projects? That's the focus here. So I first want to introduce you to Gilberto. He's the guy in the red circle. There he is. Okay, so now that you've met Gilberto, I want to also put this in the context of a figure that is a bit dated now, but this is sort of, at the time, my view of the informatics world, of the Specnet realm. And it's an attempt to sort of capture some of the different aspects of what we're trying to do in terms of data management. And I'd say historically, you know, most of the emphasis within this community has been on this part over here, developing data processing software. And it's probably fair to say there's lots of examples of data processing software out there. Some of us share it, some of it develop our own. You go to the Specnet website, there's stuff you can get there. There's other stuff in development. So that's been a big focus, and I'm not going to spend a lot of time talking about that today. What I want to talk about more is this sort of realm, the actual databases, for example, spectral libraries, the metadata databases. The take-home message, one of them is metadata is the key. You know, it's hugely important, especially when we have this kind of community and the diversity in the community. We need very smart and rich approaches to metadata. And then, you know, of course, on the right, you see there's all these ancillary databases. What matters is not getting your data into a database or being able to use it, but how we can relate these different things. Because what we're really asking about, how does spectra vary in time or space or with some other variable, and a lot of that's captured in the relationships between spectra and other types of things, for example, flux data. So, and the other point is we really need very clever visualization tools, analytical tools, so that's going to be one of the themes, is what are some of those tools? Because, you know, without those, we really can't see what we're doing, and we're human creatures, we're visual creatures, and if we don't have good visualization tools, a lot of this doesn't really work very well. So these are some of the themes I'll be talking about. And when I mean focus on themes, the focus really is how do we relate spectral data to flux data, for example. That interaction and how we develop that is really an important part. So the links between these different types of data. And I'd like to argue that we really need to kind of be working on all of this as a community. So I hope some of the ideas here will resonate, and you know, I hope to get some feedback, and hopefully we can build on some of these efforts. So a little bit about GeoChronos. It was a funded effort in Canada. It had several PIs from different disciplines, ecology, remote sensing, GIS, and vegetation and computing science. And one of the problems here, I think, and you know, advantages was we had a diversity of people. The problem was we had a diversity of people from different disciplines with very different cultures and different ways of thinking about how we do a project and what our goals were. And there's a strong technical team, computational team. Gilberto was part of that team. And there, for example, real different views between the computing scientists and the domain scientists about what we were even trying to do. The computational folks had this idea that if we could create a Facebook for scientists, everybody would come together and just magically do great science. And the scientists and domain scientists said, well, we already have Facebook. Why do we need a Facebook for scientists? Or we have LinkedIn, or we don't need another social network. We need tools, and we need clever ways of using tools. So I think what kind of emerged was an interesting elements, combination of those elements in what I'm going to show you. But it was a challenge. So what is Geochronos? Well, or what was it? It's an interactive set of tools for Earth system science. And I should say that this is no longer funded. One of the, we were talking about funding quite a bit. That's one of the challenges. So how can we build on these things that have short lives is one of my points, because a bunch of tools got built and the project is over. So how do we capitalize on that and carry on? So some of the features I'll talk about: interactive application services, Modus workflow module, where we can create regions of interest and extract time series from those. Spectral libraries was a key focus, and I'll focus most of my attention on that. And it's really the metadata tools and capabilities surrounding the spectral data that I think is the real exciting thing here. And then lastly, I'll say a little bit about how are we trying to sort of reap some of the benefits of what was done in Geochronos and make it available through Specnet-Eurospec. And these are data processing, visualization, and analysis capabilities are some examples that I'll show you, part of Gilberto's ongoing work. I should also say, the next talk probably should come first, because Andreas is going to talk about databases, spectral data, and that's kind of at the core of a lot of what I'm going to talk about, even though I'm not going to spend a lot of time in details on it. But very quickly, let me run through these three features under the middle here. First one, interactive application services. The idea here was to have a shared remote desktop that serves desktop applications. So wherever you are, you could get on a computer, no matter what platform, and run software. And so there was all kinds of software tools that we were putting on this service. And so it didn't really matter where you were, but there was a long list of things we were putting there. A couple of things that might be useful to this community: spectral index calculator, multi-spec, a processing tool. We had a bunch of Modus visualization tools that aren't shown here, because the list is much longer than this page. And so TimeSat, Lars Eklund's program was up here for analyzing time series data. And so we worked with people to let them put their software up here, and a lot of people were very willing. We ran into trouble with commercial software. They didn't want us to put their software up here. So a lot of licensing problems got in the way of doing what we really wanted to do. But at least for people's own software that they wrote, this was a very nice way to go and have access to tools. So, the Modus data processing was one area of effort, and this was we would acquire Modus data. These tools would acquire Modus data, run the Modus reprojection tool, apply a mask to create a shapefile, and then go on to create time series from these. And again, one of the main themes here is taking spectral data, but then analyzing it in the temporal domain was a common goal. So moving to the temporal domain was a big focus. Here's an example of a shapefile from a tropical site, one of Arturo's sites, and the point here was, this is Mata Seca in Brazil, I guess, and we could create any shapefile we want and extract the Modus data for that shape, which was quite useful when you're trying to relate it to a particular field site. This is a little different from the ASCII subset tool, because we could control the shape and match it to a field site. So there's a lot there that's worth looking at, but I'll skip over the details. And say a little bit about the Spectral Library. It could store spectra, and rather than a single library, what we were doing was creating the capability of having any format spectral library. And we tested this by downloading existing spectral libraries, a long list of them. Plus we created some of our own, and ended up with the capability of accommodating just about any spectral format you could imagine. So the flexibility here was really important. And this really speaks to a community where things are diverse. You know, we each have our own spectral libraries, perhaps, or our way of storing data. So can we somehow use that rather than having to put it all into a single tool? And then you could search these. If you have rich metadata and appropriate ways of searching metadata, you could search very effectively through these. Reorganize the data or the metadata fields. We can visualize things, visualize spectra or time series, and navigate very, very nicely across these things. And these can be distributed databases. They're not all on one single server. But the idea was to use the cloud concept and have good search tools to search the cloud. So here's just some example of some of the libraries. You can see in the bottom, Aster, we ingested the Aster library. We ingested the USGS library, geological libraries. But then we also had vegetation libraries from universities, and we had a sample library from my lab that we put in for testing on the top. A lot of different, some of these were geological, some were vegetation, some had other purposes. So a good generic tool for viewing spectral libraries. So just here's the tram, for example, a very particular type or way of collecting spectral data over vegetation. And so we were working on databases for that there. And you can view the spectra. These are the raw target and panel spectra from the tram, just as an example. You can see them in this format, or you can see the calculated reflectance, and this is actually not from the tram, I think. This is, these are actually from the vegetation spectral library. This is a different library. But you can navigate through the libraries, and the nice thing is you can create, each group can join Geochronos and create that group's particular library and only have access to that group, have it private as a working space, or you could make it public and have universal access and make it completely open, and all sorts of levels of control in between, so people have control over their data if they need it while they're working on it, or they could eventually make it public. Rich metadata. So you'll see these tabs above this picture. You can see this is a spectral view. Here's the metadata view, and then under that is vegetation spectral library. These are some of the metadata fields. These are very editable, and you can reformat them, you can reorder them, and they're searchable. You can see on the left, you can search through the spectral library in terms of spectra. You can search through the metadata at the same time, search different ways. And you can create a schema, your own schema. You can edit the schemas for creating any kind of spectral library you want. So there's tremendous flexibility, and we were exploring how could we use these kinds of tools for really accommodating a very diverse set of needs within the community we represented. And I think even within vegetation, this is going to be a challenge, and I think a useful concept as we try and define what are the essential metadata and protocols. So you could put in a protocol, you could put in calibration information, all kinds of things. It could take flat files as well as very structured data. Here's another view of what we called ancillary data files, and these could be anything. In this case, they're pictures, but this could be flux data. We never got very far with the flux data because that was a goal and the project ended, but we were starting to work on how do you input flux data and integrate that with spectral data. So I'll get back to that theme in a minute. And you could locate it on a map. You could see where you were on a map with this kind of image, with the map tab. So these are some of the kinds of capabilities built into the spectral library feature of Geochronos. So I think there were some unique or very useful features here. I don't know if they're exactly unique, because I think other people are thinking of these things too and doing similar things. But it really was envisioned as a collaborative environment, where people from different earth science fields could, a group within that could agree on a collection of metadata fields. And from all of this, we were hoping we could let this evolve. If you had a diversity of things, just like evolution, you need diversity, and you can see what comes to the top, what evolves over time, rather than trying to specify the answer in a top-down way. This was a bottom-up, let the community decide, and let's see where this goes. It was designed to be an organic tool. And really a key was the automation of metadata generation. so you could, in processing, for example, generate metadata automatically, which could help track what happens to the data, the provenance of the data. And so it could help keep track of where did the data come from and what was done to the data en route to its final destination in an archive. There's all sorts of tools for aligning and merging and comparing different standards, and a lot of this was metadata focused. So very flexible system, and I think that was it was a challenge, but also one of the interesting features. So I'm cutting this pretty short. Gilberto had a much longer talk. It wouldn't have fit in. So what did we learn from this? Well, I think we had some cool tools, powerful tools that could be helpful to a community like this. Rich metadata capabilities were really at the core of that, and flexibility. On the other hand, I think you could say this project was a failure in most respects, partly because we had a very diverse group of people who could not really agree on what we were trying to do. We had geologists, we had biologists, we had computing scientists, and there were real cultural differences. And I think in Canada, for example, there's this emphasis, research has to be related to industry. And I see one of the things that's happening is there's a culture of protecting everything, like IP protection, protecting your information that's tied to that. And so we had everything from the feeling we should not share this with anybody, we have to get it perfect before we can let it out, to the opposite philosophy, which is we should just make this available in all its imperfections and let the community beat up on this. Well, because we couldn't agree, we never did make it fully available. It's all, you have to have passwords to get in, and it really never reached the goal where we could have the community give us good feedback. And that was fairly frustrating, because without the ability to engage this community, which was our purpose, or my purpose in doing this, I think we couldn't really get effective feedback. So I'm looking for that feedback. I mean, if you see something here that resonates, what we're trying to do is capture the useful parts and move on outside of geochronos, because the funding has ended. Metadata is a key topic of, that we have to discuss in this community, other communities doing similar things. And there's all sorts of different kinds of metadata. There's why do you do your study, the theme. There's all the metadata associated with the instruments, the calibrations, the protocols. There's what you do in the field. There's what happens when you process your data and keeping track of what happens along the way, the provenance. So it really is a very rich area of research, I think, trying to capture all of this in databases in a way that is searchable. And I think that idea of building on that would be useful to think about. And it's a big challenge, because when you look at these sessions here, there's so many different things to think about. How do you put that in a box? I think we do need a diversity of approaches at this level, of flexibility at this level, at this point. I don't think we're mature enough to be able to say, here's how you build the perfect database. Although I think Specio is a pretty good one, and I think it's exciting that, if we can agree on using something, that's a really useful start. But what we build around that, I think, is really key. The visualization, the analytic tools, and the metadata capabilities. This is Gilberto's current view of the figure I showed you before, sort of a data flow, workflow, and he's focusing a lot on the metadata issue. I think that has to be key. And we're focusing a lot on these themes here, how you relate spectral data to eddy covariance data, and how do you relate, say, broadband sensors? How can you integrate these in an effective way? So I don't have time to go into the details of that. I mentioned a bit of that yesterday. But in terms of the data tools and the visualization tools, I think we need visualization tools for everything. In other words, at every level, we should be building tools to help us see what it is our data are telling us, or what we're doing to our data. And if we can do that, that really adds value to what we're doing. So this particular example of just taking optical data, whether it's broadband or spectral data, and trying to ask questions about carbon flux. I would like to argue that we get better insights into carbon flux when we add the optical data. So I think we have to think about making recommendations to Ikos, for example. Otherwise, things will be limited in terms of what they can accomplish. So here's just an example of Gilberto's current effort. So if you go to the Specnet website, it looks kind of like this, except you'll see none of these details because everything he's doing here is offline. But we're hoping to get to these capabilities accessible. So your feedback to this work in progress is really important. So you can visualize a site, and from those site locations, go in to look at the data available for those sites. That's the concept here. Here are some of the metadata about different kinds of sensors available at a particular site. Many different optical sensors are listed here, just to give you kind of an overview. Here's a visual view of a time series of optical sensors. In this case, it's incoming PAR and reflected PAR. And so you can create time series of raw data or processed data. And so here's just the sort of many diurnal PAR scenario, measurements from a weather station, something you might use in a model, for example. And here's the NDVI data from broadband sensors. And this is what it looks like when you just plot all the data. So we look at the raw data, and if you apply filters, a lot of what he's working on is filters to turn that into that. These are the same data sets from 3 different brands of optical sensors for measuring NDVI. And then suddenly you can see the pattern here. It's hard to see it here, but it is easier to see it here. And you see there's offsets, and you see they kind of measure the same thing, and there's some issues at the end of the season. So I wouldn't say this is cleaned up data, but it's just a filter to look at the middle of the day has been applied. So we're just looking.
2 minutes, please.
Okay. So, and that same concept is shown here with raw data on the top 2 panels for NDVI and flux data, and then filtered data on the bottom. So these kind of visualizations are very helpful. This is showing growth cycles of an alfalfa field. And so he's doing a lot of work on this kind of thing. And here's comparing ground NDVI to MODIS NDVI for another site. So these kinds of tools are being built. So I guess that's pretty much the end of it. I'd really appreciate any feedback, or I'd like to hear from groups here who are doing similar things. And I'd like to leave with the idea that I think there's a role for Eurospec, Specnet, these kinds of groups as a forum for communicating what's happening in this area. I think it's going to be hard to develop a top-down approach, but maybe we can stitch together some of the separate efforts. And if we continue these kinds of meetings outside of the meeting, I'm hoping we can use virtual meetings to kind of keep this discussion going, to create, take all these pieces and make them truly useful to the community, so the interoperability and the utility of combining these things. And I think maybe I'm over time, so I'll just stop here, and thanks very much.
We can continue this discussion in the afternoon session because the data sharing is one of the topic of the working group 1. So if you have a really short question, you can do it now. Waiting that Andreas adjusts his laptop. Do you have question? For John? Mike.
Standard.
There really is no single standard. I guess we're kind of following.
It's just I think this is you make your own metadata categorizations.
Yeah, I think that's really fair to say, and we're trying to take the separate efforts in the community and try to put them together using this kind of approach, as opposed to declaring top-down standards. I think we've tried to declare standards.
Yeah.
It hasn't been possible because of, right away people disagree about standards when you try and do them. And without the ability to fund that from a top-down approach, it hasn't been possible to declare this is going to be the standard. So we're trying a different approach. We'll see
Okay.
if it works.
Thank you. Andreas Pini from the University of Zurich.
All right then, hello everyone again. So I'm going to go on about spectral databases. First, I give a bit of an introduction definition. Then I'll show the current technical and conceptual design of the system and showing an application of this system for the summer school data, which was collected last year. So practically, if we look at the steps we run through to generate, in the end, information and knowledge, it's very clear we start at the signals level where we've got an interaction of radiation with matter, and in this electromagnetic space, to transform this information of that space into data, we use sensors, and the sensors govern the representation of the true electromagnetic signal in this data space. So eventually you'll end up just with a bunch of binary files or text files, whatever, that include your spectral information and metadata. Now, to get useful information from data, you need to do some structuring, editing, processing, and in some respect, a spectral database software can actually help you in automating certain aspects of this. Once you've got information, you synthesize this and you should come up with a journal publication. Now, as you move from the signal space up to your journal publication, you will add order and structure, value and meaning. And practically the idea is that you, as you do this, like also in this information step, you might produce products, and practically at this step, it's the spectral database software and user specifically written software that actually produces that information. So what the general goal should be for the community is to realize that the spectral database is not sort of taking away valuable research time, because you need to enter the data. It will, if properly handled, it will be a powerful tool that will actually speed up your generation of knowledge. Okay, so the definition of spectral database is pretty simple. We do store spectral information plus associated metadata in an organized fashion. For a lot of people, I think the spectral information has been the primary focus. However, and the metadata is just somewhere attached to it, and it's a minor nuisance in the best. In fact, I'd like to put this focus away from the primary resource. I would argue that the primary resource, you could say, is the metadata, because the metadata essentially defines the context in which this spectrum lives, if you like. Now, they are the key to long-term data usage and data sharing. And in a previous version of Spectio, I had 41 metadata parameters as a standard, if you like, schema. And I've opened this up to have essentially unlimited number of attributes. Technically, this system is based on a relational database server with a certain schema, and then setting up the schema is kind of not the hardest part. I think the hardest part is on the software side. So software side, there is a application written in Java. This is the main interface to feed the database and also to retrieve data from this storage system. Then there is what I've invested a bit of time lately is to use some Java components of this above software here within MATLAB. So you can do a direct data access of the database through MATLAB, And what is also possible is you can access this via ODBC from ArcGIS if you want to visualize your data in a GIS fashion. If we talk about like this, you might call this bridging technology, MATLAB to a relational database, then this would also be possible for IDL, as I'm told, and also for R, although I haven't tried that so far. Essentially, there are a few components to such a system. The first one is the storage, so that's given by the relational database and the coding schema. Then there is quite a bit of software for the data input. There's 3 stages which you can identify. The first one is data loading. So you want to load your spectral field data into the database. Then metadata editing. How do you augment your metadata that has been automatically extracted from your files? And instrument administration. How do you keep track of instrument like the sensors themselves and also reference panels? And last but not least, you want to be able to retrieve information from the system, and for that you need powerful tools, because the number of spectra within such a system are going to be large, essentially. Growing hopefully over time as people add information, so you need powerful tools to retrieve information. Where do we get the data from? This is obviously not a conclusive list, but it's sort of representing what we consider as standard inputs. So obviously you've got the sampled object. This will give you the primary information, which is the spectrum. Then GPS location, this can be done automatically for certain systems if it's attached to your spectrometer or sampling laptop, as is the case for the ISD. You put in photos of whatever you might deem necessary. Weather information, this is currently manual input. If you would have a weather station, you could write a little reading routine that would do that automatically. Biogeophysical parameters, you can enter this into the system. The automation is a matter of how you would capture these data and how you would link them automatically to your spectral information. So this is a bit of an untackled field so far. Instrument settings, these are extracted automatically wherever possible. Reference panel pool, you could enter your reference panels into this pool and track them over time. If you had a lab protocol and a field protocol, these connected together would enable to monitor the performance of your reference panel over time, giving indications when you should clean them and have them recalibrated. Instrument pool, this also tracks the calibration of these instruments over time. Obviously, the temporal aspect is part of the metadata, as is the sampling and illumination geometry. And last but not least, the user could enter any information on land cover, further target properties, and so on. Now, the concepts of data input, I think, are crucial to the whole system, because we had a first version of Specio back in, I believe, 2003 or 4, which was never really used because it was just too cumbersome to enter data. So this is key to the success of a system, to have automation to the max. And what this is doing is it's got special readers for a various number of spectroradiometer files. And we are actually also extracting what I call user-defined structure. It's just your folder structure is in a way metadata, because it represents your general idea of the sampling scheme, probably showing a certain maybe site structure or temporal aspect or whatever. In any case, we do read this information, and we also extract all possible metadata from the input files, and this is all inserted into the database. Okay, now you've got it in there. The question is, how do you retrieve data again? And the concept is to use what we call metadata spaces. So essentially, every parameter you use to describe your data set is one dimension of such a space. This is the example of a three-dimensional space made up of a target type, of a long and latitude. And now, to find information that complies to a certain value range within this three-dimensional space, you start putting restrictions on these dimensions, and all the spectra which will comply to your restrictions will be contained within this green cubelet in the middle. And if you extend this to the multidimensional case, you've got about maybe 40 metadata parameters. You've got 40 descriptive variables that can help you find your data again. Practically, this is the user interface to do that. It's sort of containing all possible metadata parameters as input fields. So you're just going to specify a certain range of values, for example, for the latitude or for the time or the campaign or who was in the investigation or sensor zenith angle ranges, illumination, and so on and so on. Essentially, in the background, this just forms a huge query and carries out this query online, so you'll automatically see how many spectra comply to this restriction of metadata space. So I'm not going to go into details of other possibilities of the tool due to time constraints. So what I'm going to show now is a case study how I'm storing spectral information plus other derived data which were collected last year in this summer school of this cost action. So the architecture setup is I've got a virtual server at the University of Zurich which hosts the database. Then there's also a web server with some pages that give you information about it, and the real data access, input and retrieval is via the standard Java application. For data access, you will need a username and password, which if you like to have one, write me an email and you'll get it. Otherwise, this data is not accessible to other people. The data I got for this little case study I got from Mikol. So practically, there's a number of comma-separated value files. These contain the wavelengths, the wide reference spectrum, target spectrum, and the calculated reflectance factor. Then there's also a bunch of raw data, which I didn't really look into. And this is interesting here. This is a metadata file which contains additional metadata, can be, I believe, date and time, and also things like retrieved indices calculated on the reflectance information. So, okay, that was what I was basing on. It also had a certain data structure on the file system. In any case, I wrote a little reading routine that ingests these data into the system. What you essentially get is a campaign, so all the data is contained within this campaign. Then there is the folder where the data was sitting on the hard disk. That's just the same name. What I do then create automatically is folders for the radiances, for the targets, for the references, and for the according reflectances. So this is done automatically. What is also done automatically is metadata loading. So practically here, for the example of reflectance, we've got the correct unit. We've got the illumination source set as sun. Then we've got a number of attributes here, cosine of the solar zenith angle, and various data quality indicators, which were extracted from the metadata file. Also, sampling geometry and illumination angles are read automatically. So this already gives you quite a good chance to actually retrieve your data again based on metadata space restrictions without any manual interaction with the system so far, apart from clicking load. Now, you could, if you know what you're doing, you could just use this automatically, like augmented hierarchy here. Just browse through, select your data, and then you could go here, like show a report with just a plot with all the metadata fields listed, export these data to a file, for example, comma separate value or NV Spectral Library. You could do some limited processing or just do a spectral plot. Okay, if you wanted to be more fancy about finding your data, you go to this query tab and you could say, okay, I'd like to have illumination zenith angle 40 plus minus 5 degrees. I want just reflectances. It should be captured with this particular sensor here, which I defined for this exercise. And then this query is carried out in real time, and you see 41 spectra within the database are complying to these restrictions. Then here we go. This is what the data output would look like. You just specify the file format and it'll be written to your hard disk. Well, actually, the file output might appeal to some people. I quite like this new possibility to access data from MATLAB. So this little script here, I'm not expecting you can really read and understand it right now, but all it's doing is it's using Java components connecting to the database. Then you can specify a query and it's automatically generating these plots here, which are just like three-dimensional plots showing the change of spectrum over time, or here just a plot showing like all the spectra stacked on top of each other. What is also possible is to visualize the numeric metadata, so you can easily retrieve here. I'm retrieving get all attributes that are called FA_par plus FT_par. And then I'm also retrieving, I believe, something like, I'm plotting this versus the reflectance value at band 500 for no apparent reason, just as an example. And what I do get is this scatter plot. So practically, you can very easily extract your metadata again and also start to analyze it in the context of your spectral information.
2 minutes.
Yeah, this is perfect. So if you want to check this out, there's this web page I set up. It'll explain how you get access. There is an online like overview of the available data. So this is just the summer school information, little case study of roughly 300 spectra. And besides that, if you want to test the Spectral application, you can go online to www.spectral.ch. You can open an online account, download the Java application, and access the online database from your local machine, and just do a bit of testing. So that would be that, and I think we might go into details on specific questions in the afternoon discussion.
Okay, thank you, Andreas. Do you have questions? Javier?
Do you know, or do you have any knowledge about what kind of things is people doing with this data? I mean, you go to a database, you get some data, but how far do you know? Where do they come from? How far do you know? I mean, people is actually using this data for, or relying on this data to do things. I mean, I don't know. I have no experience on downloading other people's data and working with them, so I don't know if people is actually using those data, or is there a kind of, people that doesn't trust that maybe the data are fine, or these kind of things, or do you have any kind of quality flags for data maybe?
Yeah, this is a very good point. I usually like to point out that what is your prime criterion of trusting other people's data? I should think what I should say is if you've been to the field with them, or if you've been to the pub and had a beer and a good chat about it, you might be trusting the data captured by such a person. In all other cases, it all comes down to meta information. I do know that a few people have asked me specifically, have you got any information on, say, multi-angular information, BRDF data sets over cornfields or wheat fields or whatever? And yes, we have that. And because of the metadata, and because this can be linked to a PhD thesis or a journal referenced paper, people have used that to validate the algorithms. But generally, I don't know what people are up to. I'm not keeping any track of what people do on my database. I believe quite a few people just like to try it out and see whether they can possibly use it. Other people might just use it to convert binary ASD files to comma separated value, You can also do that.
Okay, thank you.
Just a quick question. Is there feedback from your side if I give in data and, I carry out everything with the Specchio? Is there feedback for quality control, or a feedback which would actually help me with the processing of the data and all that?
There's one thing I support, which is, I'm not going to write you an email and tell you, look, your data's really, really useless or something like this, or is not up to the quality standards. There's one thing which we've got here, which is like a quality level. You could, that's just the definition of mandatory metadata fields. And if you click, I want to have this quality level, then it'll show you which meta parameters you should fill in order to comply to this. And this will then show as a flag in your metadata whether you comply to this or not. But other than that, what I could point you to is some recent work done in Australia, which is not yet published, but the general idea is to have an automated evaluation of metadata quality. So you get like the red, green flags popping up. And essentially it's, if your data sets are well documented, you give a chance to the user to estimate a certain data quality. It could still mean that your spectra are useless, but at least it'll give you the context of data acquisition. Yeah.
Okay, thanks. Okay. In this presentation, I will give you some detail on the European Flux database and on Ikos portal. This presentation instead of Dario Papale, the coordinator of my laboratory at the University of Tuscia. And the European Fluxes database cluster is an initiative to improve the standardization, integration, and collaboration between different databases and different projects about ecovariance in Europe. In particular, this activity started with Carbo Europe in maybe 2004, and into this database participate different projects as Ikos, Carbo Extreme, Carbo Italy, Carbo Africa, GHE Europe, and Ingos. This database provide data, ecovariance data, but also meteorological data, ancillary data, and some meta information directly provided by a PI by the principal investigation of ecovariance sites. In the Carbo Europe database, there is a really well done and developed method to import the data into the database, and each PI that want to register his site to the database must follow this and agree with this scheme, and also with the policies that is and sign the policy of the database. Here there is the map of the site that at the moment are registered to the database. Data from Carbo Europe database from 2004 and 2008 are free at the moment, and you can free download just to log in to the European Fluxes. And but data that are currently collecting in the ecovariance network are not open, and you must request to the PI to use this data. In the web portal of Carbo Europe, there is the page for each project, and there is all information of the aims of the projects, and also the result obtained by the project. As you can see here, this is an example for Carbo Africa project. There is a brief introduction of the data and how a file can be uploaded, and how to log in to this portal. And there is also an indication of the type of a file and a variable it is necessary to send to database, and it is important to follow this format. The data can be submitted as a ASCII file or using an Excel template that can be downloaded from the portal, and the PI can follow the story of the data, so can check the quality of the data, and also the status of elaboration of the covariance fluxes, and if the other people use the data. This is to make really open the use of the data, and also to make the use visible for all the community, and also for other scientific community. Data are imported to the database in SQL language, and all routines are developed in past in MATLAB and now in C environment. At the moment, they work a lot on the covariance and meteorological variable. They develop a lot of routine to assess the quality of this data, but they need some help to understand the quality of spectral and optical data for routine measurements. So in my idea, the Eurospec cost action can help European database at this stage to provide the support to check the quality of optical sampling. And here there is just an example of how the variable are named into the database. There is a root part where is the variable code, and online there is a list of variables that can be sent to database, and this list. In this list, there are also ancillary variable, biophysical variable, meteorological, and covariant flux variable. After this root part of the name, there is three different identifiers. The first identifier show the position of the sensor in a 2D space, and in this case, the root name is TS, and it represents the soil temperature for three different positions. And the second part, identifier, represents the depth of the measurement of the temperature. So first depth, second and third depth. And the last identifier represents the replication of the measurements. So this type of naming is used at the moment in Ikos demo experiment, and it will be used in future in all Ikos portal. So it's really important to give for each variable a metadata description where we can indicate the sensor specification, position, calibration, and also to give some information about the disturbance, frequency of measurements, frequency of treatments, and that all this information can help to understand fluxes and annual carbon and carbon budget. So, and this information are required also to quantify the variability and uncertainty of the covariance fluxes. And maybe this, the all information contained in metadata can be used as input parameter for some ecological models. In IMEC project, there was a part linked to near real-time transmission of the data. There were more or less 33 sites that collect data and daily send the data to the central database. And here there is an example of of the sensible heat for different sites, and this data can be downloaded from the database every 2 days. And this is just going in this part and export the CSV file. At the moment, for Ikos experimental phase, there are 123 variable, but we can add other variable, and this is a really open structure. So we can ask a reflectance variable, add reflectance variable if we think it's important to give this information to eddy covariant flux. Mailing, there is site metadata with all information linked to setup. There is meteorological, atmospheric, eddy covariance fluxes, and also hyperspectral data. All this information is contained in the database template file, and there is also another really important file that is the BADM file, and it's a file where we can send all information about respiration sampling, for instance, ancillary data on carbon, nitrogen pool, net primary production, soil characteristic, vegetation characteristic, and this is a file and used as standard across different networks. And for instance, in Ameriflux, they use the same data file. So in Carbo Europe, we prefer use this type of file and to maintain the same name of variable and the same type of number of sampling and type of elaboration. In the European data, in the European carbon database, you can find data processed at a different level. There is 3 important levels of processing for mailing for eddy covariance fluxes, so for carbon fluxes. The first level, level 2 data, this is data with a quality check given by PI, following a standard procedure of quality check in the data. And the level in the level 3 data are obtained from the level 2 products, but in this case there is a quality check procedure well documented in Papal et al. 2006. And at the end of level 3 we have data set with the flags. These flags can help to understand the goodness of our eddy covariance data. And at the end, there is the level 4, where data are U-star filtered, gap filled, and partitioned, following the standard procedure proposed by Reichenstein, Papale, and other people in the eddy covariance community. So, moreover, level 4 data are also aggregated for daily and monthly time scale. In the Ikos portal, there is also a new philosophy that can be helped to calculate fluxes and uncertainty linked to fluxes. In fact, in the Carbo Europe database, data are acquired at half-hourly resolution, and but there is no information on raw data. The raw data is data that are directly registered on at the covariance site with a frequency of 10 Hz. And now in Ikos portal, these raw data are involved and processed using a different processing scheme, also for doing some important and fundamental correction of fluxes for quality check assessment, the turbulence, the low turbulence period, and to gap fill and partitioning the fluxes. At the end, from all these elaborations, there is different versions of the same database, and by this really big database, and we are able to estimate and redistribute the data set, and to have an estimation of the uncertainty of annual carbon budget. Here there is only an example of the estimation of the uncertainty for one site. Here there is annual in EE for a time series, and the yellow circle represent the whole value of NEE obtained from Carbon Europe database, and the gray area represent the spread of the annual NEE using the different method of partitioning and U-star filtering. In fact, by the model efficiency is calculate the reference, the GPP for each year, and in the graph is represented by the blue line. So blue line in the next future in the Ikos portal, we can download the reference NEE, and then reference GPP and ecosystem respiration for our sites, and also other estimation linked to different procedure of gap filling, partitioning, and U-star filtering. In the European database, there is a policy linked to the data assets and the data use. The data assets regulate the access to the data, and the data use regulate what a user can do with the data. So sometimes people can use this data just for personal use, and can use to validate or to control, to verify published results. In this case, the policy is linked to data use policy. In the other case, when people want to publish this data, there are two options. One is to request the data to the central database, to the PI of the site, and to ask to the PI if a scientific collaboration in the paper, in the work. In some cases, data are totally open, and people can use this data without involve in the activity the PI of the covariance sites, but just acknowledge the PI. So in Ikos, the problem they use the open policy. They will open the access of the data. Yeah, Arnaud gave us a lot of input from Ikos, so I would like to pass to the part linked to activities, because in Ikos there is different working group activity. At the moment, maybe there is 4 different working group. One working group linked to edicovariant fluxes and storage measurements. One linked to flux footprint analysis. Another one linked to instrumental issues. And at the moment, there is no working group linked to reflectance measurements. So in the future, they are open, and they would like to add also this working group on reflectance measurements. And if we'll be interested, we can try to keep in touch with Ikos. I hope I well understand, Arnaud. Of course. Yeah.
For example, there are work group on ancillary data on lie and biomass measurement, and it will be very welcome because we have our experience from Carb Europe and so on, but people making validation from satellite have no experience with lie, and there is so much nothing on some variable about protocols that really these groups are open. You can register here to enter, and people from this community are very welcome, and I would say even expected for some stuff as lie and as especially for vegetation measurement, I think.
So we can.
They are just starting now. This working group have been set up since May, so they are just organizing.
Okay, there is no yet the coordinators of this working group. This is my last slide, just to see you that the new philosophy of Ikos portal, because and to explain that why it is important to have a centralized processing of the data, and why it is important to have an estimation of uncertainty. In this case, there is the cumulative trend of alpha-hourly NEE data for a site. In red, there is the NEE calculated by PI. In the other cases, is the different procedure applied by the Ikos demo experiment, where there is some options. In P1 represent the option with no angle of attack correction, P2 with the angle attack of the correction, and other filter made by a central database. This is just to say that in red is PI elaboration, in green is the different elaboration, and there is some discrepancies between the different procedure. So it's important to have the estimation from API, but it's also important to look at different methods, and this can give us a percentage of the error in estimation and EE. And this is so it's important to know that the central database processed the data without any information about the elaboration of the PI, but just know all information about the setup, use it, the instrument, and about some important metadata linked to eddy covariance fluxes. So Ikos at the moment is interact with different international projects as Neon and other as Flux Net, Flux, and go on. So in the afternoon we can discuss about this Ikos portal, and I can give you more detail on it. So if you have a question, or if you don't have a question, we can move to the last speaker of this session, Suresh.
So I have a tough job. I haven't met anybody who's said that I love to do data and metadata. So to talk about data management well into lunchtime, that's going to be a tough task. So, but I'll try to make it really quick and just kind of talk about the concepts that have not been mentioned before. I'll try to reiterate some of the ideas of data management which are really important. So there may be some repetitions, but I'll try to make this quick and get us to lunch. So data management considerations for Specnet. So really, I put in Specnet, but the ideas of data management apply to all data which is basically coming in from the ground. I see several of you over here to be both data users and data providers as well. So some of the concepts over here would apply to any data which is actually coming from research. And what I'm trying to do is to basically break down data management into individual components, and I'll just illustrate them as those individual components. So just quickly, here's the outline of the presentations. I'll give a quick institutional background, primarily talking about Flux Net, and give the data management concepts, and then I have 3 tools which are very relevant to this community. So I'll have a brief introduction to those tools. Several of you are familiar with the Modus tool, but there's a couple of other tools which I think are relevant for this particular discussions, and I'll try and elaborate them in my talk. So I'm from ORNL DAC, and without getting into details about the acronym-rich world that we live in, you can Google ORNL and DAC, and there's lots of information over there. So what I'll talk about is just primarily FluxNet, just to give you a quick, 2-minute introduction to FluxNet. So there are several regional networks collecting eddy covariance measurements, and most of them are being organized by national and research institutions. So the idea that we had was to basically create a network of regional networks. And the FluxNet really is a database that basically contains information about all these eddy covariance sites. So it's a database where people can come in and find out all the sites all across the globe which are collecting eddy covariance data. And so this cuts across geographical and institutional boundaries and has this central database. And here's the architecture of the FluxNet database that we have. So we've got all the tower sites which are sitting at the bottom. Those are the really crucial components which are collecting the data, and the data processing usually done by the investigators. So the data resides within the networks. So we've got Ameriflux, Cabo Europe, and this is just a small list that I have in this chart. And what we have are just information, pointers to those locations which have the data. So say, for example, somebody wants to understand all across the globe, I want to basically see the CO2 fluxes across croplands. So you could come in and query the database and find out all the sites which fall within that particular type. And also you could query it by climate regimes as well and basically get those sites. So for somebody who's doing a global analysis, that's a critical component. What we've been finding out recently, and this goes back to John's comment yesterday, that funding is, at times it's short term. We don't know as to what happens to the data after the funding cycle ends. And what we found recently is that, like, for example, with the Canada Flux, we've been approached by them to hold the data. So they've asked us, and we are a long-time data archive. We're funded by NASA, but the goal is to basically have this forever. But of course, that's the goal. We've been in operation for more than 15 years now, and some of the other data centers have been in operation for more than 25 years. So that's the idea, is to basically have it in a long-term data archive. And so we are very happy to take that data and then have people come in and query that data set and download it and use it as well. So we've been approached by Canada Flux, and the Aussie Flux network has also contacted us to store the data as well. We've had some other Flux data in the past, like there's a Marconi data set, which we've held within our data center. So we're kind of moving into this direction of not just providing site information, but also having the data available as well. So the number of Flux Tower sites is growing, and you'll find plenty of these charts on our website, but you could see that we've got more than 500 sites and the list is growing. And we want to be able to find out all the sites which are collecting data. What are the sites which were collecting data before and are not active, and to basically be able to tell that information. And here's a map of all the Flux Tower sites. And you can see that there's some gaps within the Indian subcontinent, but there's an effort right now which is actually going on to set up some monitoring stations over there as well. This is a little bit odd. I mean, this is last year, but there's probably more sites which have come on board. So now, getting into the data management considerations, we've all mentioned in some way or the other, and in the presentations you'd have heard that data management is really critical. But what we really need is actually a plan for implementing the data management, because without a plan, it's just a wish. I mean, we all know, okay, maybe we should be doing this, but unless it's actually spelled out in a project plan, it's not actually going to translate into something concrete. And it's very simple. The idea is that we've got all the researchers who are trying to get to the data, and we want to be able to spend more time doing the analysis and less time doing data collection. We find so often that we're spending a huge amount of time in data collection preparation before we actually get to the analysis. And what we want to be able to do is to actually cut down that time which is needed for doing that data collection process. And the way to be able to do that is once you've got good metadata, good documentation, and good standards, you'll be able to facilitate that. And I'll sort of break it down a little bit further in the following slides. But really, those are the three main components. And it's really important that we make sure that all those are captured well, and to think about that from the get-go, from the moment a project is funded, before you actually start doing data collection, it's really good to basically think about these concepts. So sort of breaking down data management, the first part is the most crucial part, it's the data set. And what I've tried to do is to basically give some items to think about as you start looking into data management and start integrating it as part of your, Manuela mentioned about all these processing levels of data. So that's one way in terms of breaking out the data set, to say that, I've got level 0 to level 1, 2, and 3. But what we find is that the definition of what a level 0 product is not the same across different projects. So one way to illustrate that concept is to have these algorithm theoretical basis document. And that's what's being used by the satellite community. And so there may be a good idea is to basically create these algorithm-based documents. So these basically talk about the science behind how is a data set being moved from level 0 to level 1, 2, and 3, and so forth. And then into data structure, there's no there's no one single way in terms of doing it. But I think what needs to be done over here in terms of data structure is to anticipate how the data is actually going to be used by the users. One way is maybe you can organize the data by time. Maybe variable may be another way in terms of organizing it. Another way is by the spatial region. So there's different ways in terms of organizing the data, but to keep in mind as to how is this data going to be used, and then putting that in that sort of a format. And I think standardization is going to be a common theme across everything that I mentioned over here. And it's very hard to have one standard across such a diverse community, but as long as there is one standard, I mean, it's not a standard that that I create. It should not be by one person or just by one team, but it has to be a community standard. So as long as there is some standard by which you're basically capturing your data set files and your metadata, I think we are in good shape. I think we need to at least start moving in that particular direction. We've talked about metadata in the context of Spectral Library, but there are several metadata tools out there that we maybe be able to make use of in this particular context. I mean, there's a standard called ISO and FCDC. We should really start looking into that and then maybe adapting it for our applications as well. I think in terms of quality and calibration, I think it's really important. We find data that comes through our door and which basically says quality, I've checked it, it looks good, I'm fine with it. That doesn't cut it for us. I mean, you need to make sure that the quality is some sort of a quantitative measure. And because it's very easy for somebody to take the data and actually do some wrong analysis with that. So it's really important to actually spell out what that quality information is and how was it actually measured and what's the expectation in terms of doing science with that particular data. And as data providers, I think that's really important that to make sure that our data that you guys actually create, is not used in the fashion that it was not anticipated, or it's used in a wrong way. So. And I just want to call out some special attention to the hyperspectral data, because that's a new, from my perspective at least, it's a new set of data set, and a lot of people are kind of getting into this area of hyperspectral data. We mentioned about spectral libraries. One thing that we found from our data center is that there is no common standard for storing hyperspectral library data. Even the software tools, there's one tool within ENVI software which reads spectral libraries, and that doesn't work with ArcMap or ESRI products and so forth. So is XML format a standard for storing this data? But if so, I mean, is there a common structure that all the different organizations can make use of? When it comes to imageries, I mean, volume is a big consideration. We saw in an example the other day that our hyperspectral data was about quarter terabyte or so. But there are new data storage formats, internal compressions within HDF and NetCDF, which could be made use of. And one other thing that I would like to call attention is to some of the data which were collected, several years before. John mentioned about this ACCP, Accelerated Canopy Chemistry Program, and this was really done in 1990s, but there's a wealth of data which was actually created as part of that. About 1,000 leaf samples were collected, spectral information from those were collected in the laboratory, and those could be useful information that we could start tapping into in this context, and we should really be thinking along those lines as well. The data that we collect right now is going to be really, really useful, 30, 40 years down the road, and so it's really important that we set it up in the correct fashion. And likewise with file structure as well. We saw a good example of a file naming convention. Follow some convention. Just don't say this is my file or delete this file.txt or something like that. Just have really meaningful file names. And then some community standards which have really taken hold in the climate community. This NetCDF, the CSP, this databases approaches. But what I've not seen so far are variable conventions. The climate community has really taken this on. There is this thing called as a climate and forecast convention. The community has basically agreed to say that if I'm storing this particular variable, these are the units, and I basically make sure that, it follows these conventions, and there is a standard that people apply to, and there are tools which actually checks that my data is compliant with that convention. So that's another approach to basically storing the data as well. And the last thing in terms of in the description of the data products is to talk about data citation. This is a new area. I mean, there's and a lot of the institutions, at least within the United States, are moving towards this. The way, like, very similar to journal citations. We all get credit for the journals that we publish, and we would like to see as to who's using our papers and all this sort of stuff. The same holds true with data as well. And there's this concept called digital object identifiers that a lot of the journals are accepting these days. So these are persistent URLs. Persistent URLs provided by a data center which actually points to the data. And there are conventions in terms of putting them in. So these are nice ways to see. You can go into Google Scholar and put in your digital object identifier and say who's using my data. It also goes back to provenance. You could basically link multiple data products together and say what was the steps which were actually done. And that's actually really critical because we want a reproducibility or at least traceability. And and it's also accountability as well. So we live in an age where our science is really being scrutinized quite a bit. So it's really important that we actually start giving credit to the data where it was actually pulled together as well. And the screenshot that I put over here is just hot off the press. So the Thomson Reuters actually published this on June 22nd, just a week back. That they're actually starting to unveil a data citation index. It's like calculating impact factors and all this sort of stuff. And that goes credit to how we showcase our data as well. It's really important. And here's an example of a DOI for one of the data sets within our data center. So if you plug this into a web browser, it'll resolve to the web page which actually talks about that particular data. So kind of getting into data processing, one thing that we really didn't get into the last day of discussion was actually archiving the code. There's a lot of processing which actually goes on, and we've talked about putting in metadata and documentation for the data products, but I think it's also important that we actually start documenting our code and maybe even archiving them as well. Because some of the processing actually, there's a lot of science behind those code as well. So maybe that's important that we actually start documenting that code and saying as to how was this processing actually done. A version control is also important because that actually gets back to the provenance and traceability. And so we need to start looking into those directions as well. So say you're creating a data product, and maybe important to say that this was processed with this particular code, with this particular version number, and here's the owner of this particular code. And in terms of gap filling, there's several techniques which are out there. And what's important is for us to actually start capturing that documentation and saying who was this, who created this gap filling technique and what was the process, and basically putting that in documentation. I think flagging schemes, I think it's really important. I think it's the quality flags are, in my mind, a very crucial component. I'm a Modis guy, so there's a lot of quality flags in there. So, but it's important. Those actually give a lot of information about how this data set is and who assigns that. When you're talking about this in context of regional networks and site data, who's assigning these quality flags? Can we agree on a standardized flagging scheme? So, a user here one person has to go to like 5 different data centers and download all these data sets and then understand like 5 different flagging schemes. So maybe there's some common protocol. And again, I'm preaching a lot on protocols and standards, but some protocol, some standard is all that's needed. The same holds true with QA, QC as well. And then when you're trying to do intercomparison, that actually gets important because you're trying to do data sets from multiple regions and trying to get them the data. So finally, in terms of data management, I think the metadata and documentation are the real key. It's absolutely essential. It'll increase the long-term utility of the data. We find data which were created in the 1990s, and we still find a lot of people coming and grabbing the data and making use of them. So really plan for the data for 20, 30 years down the road. So creating a documentation should be a part of the data management. I think for people who are part of big agencies, and if you're controlling the money in terms of where it goes in terms of proposals, I think we're seeing a trend that agencies are starting to support data management. They're starting to put in a requirement to say that you have to create a data management plan as part of your proposal. What we would like to see is having a funded component to data management, because that's essential. And I think the more we start doing it and more we start adapting to that, I think it'll become a community practice. And for good documentation is essential for the proper usage of data. I mean, absolutely. And make sure that it describes everything. From citation, make sure that you get credit for the data that you've created, and what's the usage policy, and what's the expected scientific usage. I think that's also important. You as the data creator would know as to what's the applications of this particular data, so that it's not done in a wrong sort of a fashion. I've listed a couple of links to some resources which actually describe about preparing those data set documentation. You can refer to them. The first one is a 40-page document which actually talks about everything from file naming conventions to data file formats, both with raster and vector data, field data, and gridded data, and all that sort of stuff. And the other one is the NSF project called Data One. So there's several tools out there, and of course, data centers, we're very happy to work with you in terms of preparing a data set as well. So here's a summary of what we've talked about, but I'll just call out specific items in here. I've already mentioned about some of the other items. First one is actually when you're creating those data sets, make sure that the producers of the data are working closely with the data users. I think that's going to be critical. And also establish the standards. When you talk about standards, it's not just about files, it's also workflow and networks as well. So when people are accessing the data files, and we're finding that more and more users are actually coming and grabbing data from tools, so the tools actually know how to talk to the data and grab them. So there is these web service standards called SOAP, OGC, REST, and all this sort of stuff. And we're living in a world where everything is actually driven by web services. All our smartphones are all hooked onto those. So it's really important to do that as well. And then I think it's a dedicated financial support is actually important. I think can't stress that enough, because that data is actually important. So I've mentioned those. I'll quickly step into some of the tools that we've talked about. The first one is the Modis subsetting tool. A lot of you are familiar with these tools, but the idea is to basically provide Modis subsets for these field sites. So we were actually charged with actually creating these Modis land product subsets for field sites, and there were several reasons as to why we wanted to do that. One was accessibility, data format, and processing time. I mean, it's very difficult to deal with satellite data because of the large volume. So what we've done, we've actually created a tool which will allow you to provide a lat long and go in and grab those Modis land. Several of you used this tool, so what I would like to do is just mention about some of the highlights, some of the features that are coming on, the new features that are coming on board. The most important feature is that maybe a lesser known feature is that we actually do the quality filtering on the data. We've actually worked with the PIs of these land products to actually say what constitutes a good quality. So we go in and filter out the bad data and then use it as part of our visualization. So what you see over here on the right is our new ordering interface. What we've also done is to basically add these Google share plots. You can mouse over the map and actually find out what's the data value of NDVI for one particular point in time. We're actually adding a daily data product. The daily surface reflectance is going to be added. That's something's going to be coming about in the next couple of months. We've also increased the size of the subsets to 1,000 by 1,000. So for this community, we're really looking at single pixels, one. But if there's somebody who's interested in basically grabbing all the Modis data for Spain, say for example, there's a way to get that data. And we're also chaining them to R. A lot of the community, we see that R is being widely used because it's open source. It's good for statistical summary. So we've integrated the code with R as well. And you can basically grab the data from that. And of course, there is an opportunity to get the data in a JOTA format as well. So there's one other feature that's come about, at least 3 or 4 people have come in and asked me the last couple of months is, can I extract Modis subsets for multiple sites? Yes, there is a way to do it. We have a web service. There are codes which are available out there. And if you're interested in basically getting Modis subsets for multiple sites in an automated fashion, send us a note. I mean, it's kind of hard to explain that right now, but there is a way to basically write a code and extract that. So this image actually shows all the data from which people are grabbing data. This is just 6 months. And all those red dots are about in the hundreds of data orders. The purple ones are like thousands of data orders and so forth. So there's several people looking at this data in several different regions. How are we doing on time? Okay, so I'll just run through this. DayMet, there was discussion about upscaling. The idea over here is to take all the field data. There's hundreds of sites which are collecting meteorological observations, and to basically create a gap-filled spatially and temporally gap-filled data for the entire North America. And so this data is currently available at 1 kilometer resolution. It provides temperature, precipitation, humidity, and radiation as a continuous surface. Right now, it's available only for North America, but if there are meteorological stations within Europe, I mean, I see that a product like this could be created. A lot of the modelers like this because it's temporally and spatially gap-filled. And it's being used by many different agencies, and the data is available in CDFC convention. And there are also ways to basically get the data online as well. So we have a Modis like single pixel extractor, which actually goes in and grabs the data and does the plot, and you can actually look at that data. Last tool that I want to quickly mention is the spatial data access tool. So this is really important when we start getting into this idea of creating these hyperspectral images. What we want to be able to do is for people to pop that data directly into different software. And you don't have to have multiple ways in which you distribute the data. So we've created this tool called Spatial Data Access Tool. And behind the scenes, it's using web service standards. I'm not going to get into a detail of how it does that. I'll be happy to talk with anybody who's interested in that individually. But the idea is that you offer up the data, and people can visualize the data through a web browser or whatever tool and be able to download the data in whatever projection resolution that you want. And to be able to do that using web service standard that you can start. But all these tools, I mean, it's possible only because the data is all structured well. If it's not, it's going to be a tremendous amount of effort for us to do the data preparation and do that. So what we want to do, tell people that, look, we could do all these tools. John mentioned about all the need of tools for the community, but the data has to be structured well, because if not, this postgraduate student is going to be spending much of his time in research and preparing the data and staging it. So final thoughts, keep in mind that your data with standards and analysis in mind, prepare your data for others to use. Metadata is absolutely key. I mean, I'll stop there. I mean, there's some other nice pictures that other people have created in terms of the importance of data documentation, but that's the message. Thank you.
Thank you very
Mm-hmm.
These tools look really fantastic, and about this last part is the EMET, and it's really good that the North American community and the European community are gathering together, because then we can share our experiences. And in fact, there is a similar initiative as the EMET also here in Europe. It's called EOPS, and it's the product that is coming from the interpolation of meteorological stations, and they provide precipitation, radiation, pressure, and I don't remember, another variable. And maybe would be nice to see if we can link the two initiatives.
Yeah, absolutely.
Okay. Another question back there.
Just how hard would be to extend this MODIS global tool to other satellite information?
Would not be. I think it's just a matter of storage and setting up the resource. The MODIS data is stored in HDFUS. So if that file format follows some convention, that's fine. It's like whatever format that you want, as long as every single data product from the satellite follows one file format. And then the quality, that needs a little bit more involvement, because you need to understand for each of the products, how do you interpret that quality. For MODIS, it was actually a little bit more challenging task, because each one of them treated it differently. And then we also had like 3 different resolutions of the data. But in terms of training them, once after you create the subsets, all these visualizations, those could be ported quite readily. I mean, I think it should be, I wouldn't say that this is a day's worth of job, but I think we can accomplish that maybe in a month or so at the most,
Okay, thank you.
Thank you.
Suarez. I would like also to thank all speakers of this morning's session. It was really fruitful, and there is a lot of topics that we can discuss in the afternoon session. I invite to join us in this working group 1 session that is focused on protocol definition and data sharing. So we would like to start to think deeply into these topics and start a collaborative initiative with all of you. Thank you very much.